as we celebrate the 80th birthday of Николая Ивановича Шакуры. And before participants, before the first speaker, while participants are still gathering, let me give you a short overview of the main milestones of Shakura Nikolai Ivanovich's scientific career. I hope you will see this slide on the screen. So Nikolai Ivanovich was born in a small village in Belarus just after the Second World War. And after the school, he moved to Moscow to study at the physics faculty of the Moscow University. And when he was a student, he was introduced to relativistic astrophysics by Yakov Zeldovich. Back then, Nikolai was very active in athletics. As we know, he was running a lot, but he had to sacrifice it. Over the years, he made remarkable contributions to astrophysics of neutron stars and black holes. And of course, the most notable achievement is the alpha parameter and the standard model of accretion disks. So the Shakura-80 paper gave us a detailed description of the processes accompanying the process of matter accreting on a black hole. And this paper gained a worldwide fame, and it is continued to be one of the most cited publications in the astrophysics. Throughout his career, Nikolai Ivanovich worked in the Sternberg Astronomical Institute in Moscow, GAISH. Since 1990, he is the head of the relativistic astrophysics department, and he is an associated member of the Russian Academy of Science. He has received many state and international awards. For me personally, first of all, he is my supervisor who has defended my life in science. But apart from this, for me, he is an example of a pure scientist who is devoted to astrophysics. He is like a knight in the order whose motto is curiosity, non-stopping questions, and admiration for the unity of the law of nature. He always inspires everybody around him, and he supports fellow scientists in their intellectual pursuits. So today is the opportunity for us to greet him and to share the stories about astrophysics and life, and also to celebrate the open-minded spirit of science. So before further postponement, let me introduce the first speaker. The program of our conference is on the screen now. Also, it's on the second tab in the Zoom, if you like to check it. So our first speaker, please prepare to share your screen, Konstantin Alexandrovich Postnov. He is also studied in the Moscow State University and worked there for about 40 years. He is now the director of the Sternberg Astronomical Institute, and he has published a lot of many works together with Nikolai Shakura during many years. They published almost 100 papers together, and they continue to work together. So please welcome Konstantin Alexandrovich. When you are ready, please share your screen.
Okay.
I'm
tried.
stop sharing. Yes, I'm stop sharing right now.
And I can share right now. Can you hear me?
Yes.
Tak. Moment. Paper. Так. Do you see my screen? Can you see my screen?
No.
Or not?
It's okay.
Oh, Kostya, maybe
Yes.
it's another.
I see it. Sorry, wait a moment. Let me. This one.
Yes.
Oh, okay.
Николай Шакура. Do you see it? Yes.
We see it still not in the presentation mode.
And now?
Yeah.
Now it's okay?
Yeah.
Okay.
It's okay.
It's in the presentation mode.
At least me, I see it in double page, in 2 pages.
Yeah.
In 2 pages.
Yes, left and right.
Okay. So, but okay, let us do not miss the time and
Okay.
okay. Now it's see it in full details probably. I started to work. This is the first difference. First of all, I congratulate you this great day, this great how to say this celebration of our colleague Nikolai Shakura, with whom I collaborated since 1987, something like that, for almost 40 years. And this is a picture taken shortly before the COVID in 1991, when you see him sitting in our a little bit practically organized workspace, where we did with him many interesting work. So now this is a picture taken in 1991, where we are sitting with him in the same room. This is it was in the beginning of 1991. At that time he was rather young. You see him smiling, and it was some, I don't remember, this was some celebration of probably maybe even his birthday. I don't remember exactly. So we have collaborated with Nikolai with for many, I would say, for many topics. And we say we started in 1987, as I said, and in about 1990s, he attracted me to study Hercules X1, one of his most famous source, and we did a lot of work about that, but I will not speak about Hercules X1. And now we continue with young people doing some science, and we have some interesting results here, but I will not speak about that at all. But not only Hercules X1, but other X-ray pulsars we considered. And the most important achievement here was in this topic was the development of quasi-spherical accretion and subsonic accretion known to slowly rotating neutron star, which the paper was published in monthly notice in 2012. But when we were one day, I remember, in Garching, he told me that it is interesting to dig into in more detail into the so-called magneto-rotational instability. And the magneto-rotational instability, as you know, is one of the now it's established, almost established. This is one most favorable mechanism for development of turbulence in accretion disks in Keplerian flows. And but Nikolai always says that he has some how to say this, some trouble with this instability, and we try to dig into detail of this instability. First, let me show you the very famous system of MHD equation. It's non-ideal, in fact, non-ideal MHD with say with viscosity and magnetic viscosity. So it is simply to write, but difficult to solve. I don't remember. Some famous physicists said that probably in classical physics, this kind of equations remained so far unsolved problem. But I mean, they describe a lot of physical reality. So this is why we rely on this system of equations, of course. And the first thing we tried to do it was to repeat analysis, local analysis of this equation when you consider small perturbations of physical quantities, of velocities and magnetic field which enters into the Lorentz force here, taking into account non-ideal terms, this viscosity and magnetic diffusivity over here. And we did it in 2015 and use, as people usually do in this kind of analysis, so-called Boussinesq approximation for a continuity equation. The continuity equation is a very important thing here. And the continuity equation for incompressible fluid is in Boussinesq approximation is written very, very simply. You see, this is algebraic equation, and perturbations are taken in as usually in this linear analysis as plane waves. So we repeated the analysis was taken into account of the nonlinear on this non-ideal plasma and published paper in monthly notice about magneto-rotational instability in ideal and non-ideal plasma. This is the paper, and in this approximation, everything is very simple. You reduce these complicated equations to the algebraic system of algebraic equations, and they reduce to first order algebraic equations, but this is actually the quadratic equation, very easy to solve. And dispersion relations which appear here are shown here, for example, for Keplerian case, for Keplerian velocity. And you see that there are some stable Rayleigh modes, which are always positive, and there are some unstable, we call this Velikhov-Chandrasekhar mode, because the Evgeny Velikhov and Subramanian Chandrasekhar were the first who discovered this instability in the end, in the beginning of 60s, I would say. So, and then the analysis is rather simple, and it is interesting that in this approach there are no critical magnetic fields for the instability. Instability appears locally for any value of the magnetic field, and the effect of non-ideality of plasma reduces to just changing. For example, here is shown is the effect of the viscosity in some units. If you change it to increase the viscosity, then the instability is not disappear. It is present, but the increment gets smaller, and the range of wave numbers where it is operating also is smaller. important here is the range of the wavelengths k. This is the square of the wave vector. And you see that instability persists. And for us, it was interesting result. We published this. But then we ask ourselves, is it possible to by making this kind of analysis with taking into account non-idealities, but forget about the magnetic field to see is it possible to find any purely hydrodynamic instabilities in Keplerian flows? Because of course we are sure that magnetic field should be present, but suppose there are no magnetic field, then you forget about induction equations and Lorentz force in dynamical equation. So what do we see? And to our surprise, this analysis leads to the appearance of some unstable modes, even in the absence of magnetic field for Keplerian rotation, and is taken into account even the structure of taking into account the presence of viscosity. And here is some particular results for some Prandtl number, which is proportional to the viscosity. And it was so interesting for us that even small viscosity makes appear to the presence gives rise to this unstable mode. This rather, I would say, small increments, so they are not very effective. But we decided to increase this analysis to sharing flow. Sharing flow means that you have this structure along vertical direction in accretion disks, which Nikolai collaborated very well with colleague Itsaris previously. And we use this so-called analytic approximations for continuity equation. You see here the derivative of density along the coordinates appears. And everything becomes much, much more complicated. Even local analysis in an elastic approximation becomes rather cumbersome, and the perturbation are taken in the form, you see now they search them in the form of not pure plane waves, but there is some unknown function f of zeta. And doing so, we arrive to Sturm-Liouville problem for pressure perturbations. It can be solved. And as for dispersion equation, they are reduced to six-odd algebraic dispersion equations, which we also solved. And we found that in the presence of this density gradients and pressure gradients along vertical axis, temperature, everything, and entropy gradients, we found the so-called viscous convective instability. Convective because if the entropy gradient appears along vertical coordinates, Brunda-Viasali frequencies arises, and which leads to a sort of convection. So our idea was that probably the turbulence can be seen in the absence of the magnetic field because because we found this some unstable modes. But of course, the nature is much more rich than this simple approach because we always have magnetic fields. And our next step was to look at what is the effect of the magnetic field in the stratified flows such as accretion. But all these studies were summarized in our two books in Russian, Accretion Processes in Astrophysics and Accretion Flows in Astrophysics, were published by Springer in 2018, and where we very detailed analysis of all these things. And it was contribution from Galina Lipunova, who wrote, and Kostya Malanchev, who wrote the first introduction to accretion, stationary accretion, non-stationary accretion, many things. And our analysis for MRI was also summarized in these two books. And next, I said, but it was interesting for us how to deal with these magnetic hydrodynamic equations in when we consider not local, not VKB approximations, but non-local approach to MRI. And the first paper by Velikov was exactly, he used this non-local approach. And in the review by Balgus and Haile in Revmont Physics, they wrote that this is mathematically laudable because this is interesting mathematically problem, but it's not very important for MRI because local analysis for MRI is sufficient to show that it's very effective. Anyway, for some time we elaborated this for about 1 year. Elaborated this analysis, and we published the results. 2 years ago in Physics Успехи физических наук, in the Russian journal, where we considered this non-local approach to MRI in the form where this these are sign-like perturbation along z coordinates and free function f of r along r coordinates, and then from those system of equations in ideal plasma, we obtain second-order differential equation for some perturbation, say, magnetic field along r coordinate, but it can be done for any variable. And we get rid of first derivative in this equation and obtained very simple second-order differentiation equation, which can be treated as Schrödinger equation for if we treat wave number as energy. This is just Schrödinger equation for this some non-trivial potential, which we not met in quantum mechanics, by the way. And we make this analysis, but most important thing is that in this picture, you just solve Schrödinger equation with corresponding boundary conditions and found stationary levels for this value. And it gives you dispersion equations for these MRI modes. But important thing is that here the so-called critical magnetic field appears, which suppresses magneto-rotational instability. That the magnetic field should suppress a large enough magnetic field should suppress instability. It's clear from physical considerations. It was known before, but nobody calculated this before accurately. We did it for this particular case in this non-local analysis. And here is, for example, one example of this dispersion curve, and you see this negative values of omega of frequency means instability. You see there are some values of magnetic field. Here is the magnetic field in some dimensionless units. It shows you that there is a range where magnetic instability can appear. And here it disappears. Increasing magnetic field, you go into here, and magnetic MRI disappears. So we did a lot of more details in these particular papers, but for us it was not sufficient because the structure along vertical coordinate seems to be stratified flows. All the flows must be stratified. Seems to be much more important than stratification over radius. Radii could be very large, and it is something which we should do. But it turns out to be much more complicated. We tried more than 1 year to solve this problem. And of course, we should use this inelastic approximation of continuity equations, which immediately complicates the problem in such a way that instead of second-order differential equations, you obtain sixth-order partial differential equations for perturbed quantities. Nobody knows how to solve it because, because you have all derivatives, 1, 2, 3, 4, 5, 6, and you have to set corresponding boundary conditions. So you see that it's not easy to do. We tried to simplify it. We did log analysis, assuming some say velocities along that perturbations along z coordinate equal to 0. This way enables us to, in this way, we obtained a critical field for MRI, but it is, I would say, interesting, and it's not yet published. But now we are working on next step, and it turns out that for particular perturbations which are located along z coordinate and r coordinate, when we have no perturbations along phi coordinate, then you obtain second order differential equation, and this is just a matter of technique to solve it. And it's not easy, but it's doable, and we did it. And what we found that surprisingly, this is a preliminary result. MRI is absent for such perturbations for any value of magnetic field. So magnetic field compress, so kills down. It extinguishes this small perturbation, at least for this particular case. So, but this is still preliminary result. We are working on this, and we hope that the great intuition and physical vision of problems which Nikolai has and always apply when he solves many physical and astrophysical problems will help us to solve this very interesting and difficult, I would say, mathematically challenging problem. Thank you very much.
Thank you, Konstantin Alexandrovich. Thank you. Maybe somebody would like to ask a short question. Yeah, it's always like Nikolai Shakura, and at the frontiers, at the most difficult problems of astrophysics, turbulence, less understood by all scientists. So probably if we have no questions, we will proceed to the next speaker. And I see there are many students in our today's Zoom. So while Professor Staubert is preparing to share, I would like to introduce him. And Konstantin Alexandrovich, I would like to ask you to stop sharing. Yes, thank you. So Professor Rüdiger Staubert, and he is an astrophysicist known for his great contributions to X-ray astronomy. He began his career at the University of Kiel and later worked at the University of Tübingen. He worked on neutron stars, accreting binaries, and cyclotron resonance lines. He made the first direct measurements of the magnetic field on neutron stars. His work includes balloon-borne experiments and significant contributions to satellite missions. Professor Staubert has collaborated with Nikolai Shakura for many years on accretion processes in X-ray binaries, and they published more than 30 papers together. So please welcome Professor Staubert. You also have to unmute yourself. Yeah, we can probably unmute. We still don't hear you. Could you try and press the microphone again? Maybe it's just me.
Ausschalten, yeah, okay. Do you
Oh,
see now?
great, thank you. Yes, we hear and we see it's not in the presentation mode. If
That's right.
you can try to. Yes,
Okay.
perfect.
This good?
Yes, yes.
Okay, so yeah, congratulations, first of all, to Nikolai. It's wonderful to reach an age by 80. Yeah, it was 80 years. This is wonderful if one can survive so far. Now, I have worked with Nikolai for a long time, say about 20 years, since 1969. How did it all start? Actually, we first met in Australia at an IAU colloquium in Port Douglas, which is a very nice place at the Great Barrier Reef. Unfortunately, neither Nikolai nor myself had the opportunity to really dive down into these waters, which I did later with my wife, which was very wonderful. But the environment was very good. And so, of course, we knew each other already by that time from the literature. Nikolai had produced a lot of wonderful papers, especially about accretion disk and accretion onto neutron stars. Now, I like to point out this one here. Note the enormous amounts of citations there on the black hole binary paper. Myself, I had concerned myself with observing X-ray binaries, first with balloon experiments and then moving to satellites. First actually was the Mir Hexe, which we did together with Rashid Sunyaev on the Soviet space station. And our early achievement in the mid-70s was to discover the cyclotron line in Hercules X1, which, as you had mentioned, Galina, is the first direct measurement of a magnetic field in a neutron star. So, meeting in Port Douglas, we of course talked about Hercules X1 because we both were interested in this object. And so we agreed to work together and combine our forces, especially good because in Moscow, there were a lot of capabilities in theoretical studies, which I missed. Theoretical studies and modeling, which I actually had not done so far. But I had a good experience in data analysis and had made a lot of observations and data analysis. So thank you for saying that we produced 30 papers together. Maybe that's true, but the ADS just lists 25 common publications where both names, Shakura and Staubert, are on the author list. Apart from that, we did projects, actually wrote proposals to the Deutsche Forschungsgemeinschaft, DFG, and the RFBR in Russia, and received corresponding grants, which enabled us to travel and to visit each other. So we had several nice visits to Moscow and to Tübingen, of course. And importantly, we became good friends doing all of this together. So the collaboration, let me introduce the key people. Nikolai Shakura, of course, in Moscow, and Konstantin Postnov. They are both here in the Sternberg office there, which appears that there's a lot of work going on. And Dmitry Kolesnikov, which actually I did not meet in person so far. But we know, of course, each other from the literature and from other interactions and having common papers. Now, from Tübingen, it was myself and Jörn Wilms and Dima Klotchkov. Dima Klotchkov actually was a student of Nikolai's and made his physics diploma in Moscow. And one of these visits to Moscow, I got to know him, and I kind of suggested whether I could import him to Germany, whether he would like to come to Tübingen and do his PhD work with me, which finally happened. So it's Jörn Wilms here and Dima Klotchkov. Can you see this? Actually, it's blocked here in my screen. Can you see Dima?
Yes.
Yes, we can.
Yes, you can. Good. So our common science interest, of course, is X-ray binaries, and very specifically Hercules X1. And these is a list of things we sort of investigated. The accretion disk and its column, the 35-day modulation, I will come to it, what it is, neutron star free precession. Actually, this is the main topic. Pulse profiles, variability, pulse period, evolution, and so on. But I do have to say that the first point, X-ray spectral cyclone lines, we actually did nothing really together. I was not able actually really to interest Nikolai and Konstantin to go into the deep physics of the cyclotron line production on neutron stars and magnetic fields. Anyway, the other topics all boiled down to one question, namely, what does the neutron star do? Possibly, does it do free precession? So just to introduce X-ray binaries, you all know this very well. I do this very fast. So we have a binary here, and the neutron star is accreting from the optical companion, and the matter falls down along the accretion. The accretion follows the magnetic field lines, and the material is just stopped at the polar surface of the neutron star, and it gets very hot, so we get X-rays, and there's a beam emitted, probably in the pencil beam and also in the fan beam direction. Now, what are the critical observations on Hercules X1? For instance, what we do find, and we know from the early discoveries by Uhuru, that there is a long-term flux modulation on this side here. Actually, it's a 35-day modulation with the main on, as we call it, and a short on. There are binary eclipses with 1.7 days. There's pulsation because the magnetic axis and the spin axis of the neutron stars are not aligned, so we get a lighthouse effect there with 1.24 seconds. It turns out that the pulsation has a good pulse profile there, but this pulse profile is not constant. It is variable, and particularly variable with the 35-day phase. The other thing is the period of pulsation itself, 1.24 seconds. We find that it's variable. This is a plot here showing the 1.24 seconds as a function of time, and there is a general spin-up trend, but there are deviations here with periods of short spin down and over again, and so there is spin up and spin down change back and forth. And the important thing is this 35-day clock. The onset of the flux we call the turn-on. In principle, we have sort of a 35-day clock, but this clock is very irregular. It is not very steady. So the turn-on happens, there are deviations from a pure, strong clock, and this is displayed in this plot, the so-called O-C diagram, which means the observed minus calculated turn-on times, where we assume a constant period, C, calculating this by a period of, it turns out, 20.5 binary periods, which is in days, 34.85 days. And this shows here how variable this is, so it's a quite irregular clock. Okay, and this is supposed to show how the radiation receives the Earth and also its companion, H3 Hercules, because there is an accretion disk which apparently is warped and precesses. And the precession of the accretion disk sort of blocks the X-ray beam regularly such that we get the 35-day flux modulation. But what about the neutron star itself? Now, the big question for all work we had together is, does the neutron star show free precession? Now, then there was a very important observation by Trumper et al. Using exosat observations of Hercules X1, and they found that indeed these pulse profiles are systematically variable. They change their shape with 35-day phase. So since we think that the X-rays which produce the pulse profiles emanate from the neutron star's surface, it was natural to assume that these variations might have to do with the neutron star itself, especially free precession. Now, there was a nice paper in 1977 where Shaham actually made this proposal specifically with application to Hercules X1. Okay, I will not spend much time on this picture. You all know what precession is of neutron star, but the important point is that we have an offline sort of magnetic dipole field with the North Pole and the South Pole, and there is an offset from the straight line here to the North Pole. And with precession, the X-ray emitting pole moves around like this. So we should expect that while this is moving, the radiation pattern changes and produces the changes in pulse profile. Okay, I like to go to very briefly to 4 important papers. Does the neutron star show precession? In all those 4 papers, the answer is yes. And one is, I will go through these from Postnov, Shakura, Kolesnikov, and myself. So let's start neutron star free precession paper 1 from Postnov. We actually, on this, we used pulse profiles observed with the Russian X-ray timing explorer, the United States satellite, and the pulse profiles are shown here. And you can see they change their shape with 35-day phase, which is listed here on the right-hand side of the plot. So the procedure is, of course, observe pulse profiles, which actually I did mostly by proposing for RxTE observations and got all this. Konstantin and Nikolai produced a model, assuming certain model parameters in order to predict how pulse profiles should look like. And of course, the idea is to compare the observed pulse profiles with the predicted profiles from the model. Now, I cannot go into very much detail on the models or so, and there are plenty plots like this here in the Postnov et al. Paper, comparing the observed profiles, which are hard to see, which are in black, and the predicted profiles from the model, which are in magenta. And it turns out it's a very, very good fit. And this fit requires the free precession. So the neutron star free precession is okay. And more so, we have to conclude that possibly neutron star precession is the prime 35-day clock, 35 days, and apparently the neutron star accretion, the accretion disk in its precession takes up the same period, and the idea is that magnetic interaction of the inner disk of the neutron star with the magnetic field of the neutron star is responsible for slaving the disk to the same precessional period as the neutron star. Neutron star free precession paper 2 from Nikolai Shakura. He made efforts to do optical observations and somehow managed to separate the contribution on optical light, which comes from the accretion disk. And doing so, again, one can model what to expect from this precession accretion disk, processing accretion disk, and compare to observations. Again, this is a selection of a few profiles, 35-day profiles for different observations. And no, this is, binary profiles, sorry, for different phases of 35-day phase, which are shown here. So this is the 35-day phase. And again, the conclusion is the model predicted flux fit very well what is observed. And so we assume that the neutron star undergoes free precession. And the variability can be explained by forced precession of the accretion disk through the magnetic interaction. Paper 3 by Dmitry Kolesnikov and others. I'm not involved actually on this paper here, interesting. It analyzes the pulse period evolution itself. Now, this is not pulse period, but frequency. But what one can see is that there is a spin-up, a general trend for spin-up, and then a lot of local variations. And the question is, that is answered here in this paper, and this is this possibly a sign of free precession of the neutron star? And again, a model was produced to predict these variations in pulse period or pulse frequency. And again, this is a selection, one plot of lots of plots from this paper where one compares the model and the observations, and it appears there's a very good fit. And actually always, as always, from those fits, if they work, one can extract the model parameters about the system. Otherwise, and of course it has been done to optimize these parameters to make the best fit to the data possible. Paper 4, neutron star free precession by myself, basically. Again, using the pulse profiles and the change of the pulse profiles with 35-day phase. I had produced a database, actually a template of pulse profiles, typical pulse profiles for every small interval, actually a hundredth of the 35-day phase with the characteristic pulse profile. This is from a selection of data of two 35-day main ons used by, observed by RXTE. So taking all other observations RXTE, one can then find from these pulse profiles a turn-on of the 35-day by taking those profiles, determining their time, their 35-day phase, because the profile shape is very characteristic, and one can find the 35-day phase from this. Now, if one can then extrapolate back down to 35-day phase 0 and get a value at time in MGD for the actual turn-on. Now, those turn-ons produced from pulse profiles are shown in the O-C diagram with red points here. The green points are the long-term history of O-C turn-ons observed from the accretion disk itself. That means from the modulation, 35-day modulation observed. Yeah. So the conclusion, there's only one 35-day clock. Apparently, the pulse profile clock, which we think is associated with the neutron star itself, and the flux modulation of 35-day, which we think is associated with the precession by the accretion disk, is actually identical, which requires that there is a physical interaction and connection between the neutron star itself and the accretion disk. And the idea is that the neutron star precession is the prime clock. So I think from this point, the question is answered. Yes, there is free precession. I like to mention that a recent support has been found to this idea by observing polarization by the satellite XP, IXPE, United States satellite, and the paper is published in Astronomy Nature by Heil et al. And they strongly endorse this idea by interpreting their data from polarization, which is a new, relatively new, since 2 years, way of observing X-ray objects. So, to my mind, there are then two questions really to be answered. How does the magnetic interaction between neutron star and disk work? Maybe I have missed it, but to my knowledge, there is no hard treatment there, how this in principle, in detail, actually work. And so I'd like to encourage Nikolai and Konstantin and co-workers to get to this problem and solve it and describe in detail how this might work. The other question in my mind is, maybe you can answer this straight away, but there is one observation which I have not mentioned here, which has been done during a so-called anomalous low, where we find that the precessional period of the accretion disk must have been very, very low. The period must have changed from 34.8 period, which is the usual period, to something like 33.5 days. Now, my question is, if there really is a rigid connection between precession period between the neutron star precession and the accretion disk precession, this requires that the neutron star precession is actually able, as the neutron star actually is able to change its precessional period by about 3.7% in very short time scales. Very short means over a few 35-day cycles. I had published a paper in 2024. This is wrong. This is wrong. This is in 2009, actually. Sorry about this. Claiming that there are two clocks just by observing these data from the anomalous law, which showed that either the accretion disk had done an extra cycle of precession by having this short period for a period of 600 days or so, or the neutron star itself also changed its precessional period to a very low value, namely 33.5 days or so. My gut feeling is that the neutron star should not be able to do that because of its big mass and everything, but maybe this is wrong. So please let me know what you think about this, and I will revisit my early paper on this, whether I made any mistakes in there, maybe in interpretation. So that's it. And I like to say to Nikolai, take care, all the best for the future, and stay active, and hopefully we can continue to work together and to cooperate again. So, cheers. All the best to you, Nikolai. Thank you.
Oh, thank you, Professor Staubert. This is an ultimate review of Hercules X1 precession. Nikolai Ivановich.
Thank you, Rüdiger.
Thank you. So I may say, I do have a few more pictures to show from visits.
Yes, please.
Back and forth. Should I do this?
Yes,
Okay.
absolutely. Please.
Okay. So here's Nikolai and Natasha in their home for one of our visits to Moscow from Tübingen. Of course, this is Dmitry Klochkov, also, it's Natasha.
Yes.
And we have a corresponding visit of Nikolai and family. Natasha was also there, and Konstantin. This is in my home. Actually, this must have been, I don't know, in 2000 something.
2007, something like that.
2007 or something, yeah. Wonderful, and Konstantin has one of its daughters here, right there. And this is actually more recently, it's only 6 years ago, in Tübingen at the festivities to my 80th birthday, together with Joachim Trümper, and Nikolai had just sort of presented a gift to me, one of his books. Again, from the 2019 visit in Tübingen, where we had a small meeting on the occasion of my 80th birthday. Nikolai with myself on the back, and Natasha with myself on the back. And this is a very nice picture I like very much from the evening party we had then with Nikolai Shakura first, Rashid Sunyayev, Joachim Trümper here, my PhD advisor, by the way, and long-term collaborator and friend, and Günther Hasinger, who also was a very important student of Joachim Kepler's. So thank you very much. This was it.
Thank you very much. Thank you very much for your talk and for joining us today. We did enjoy this story very much.
Thank you.
So let us probably proceed to the next speaker now. This is going to be Valery Suleimanov. So originally, Valery is from Kazan Federal University, where he graduated and where he teaches the students, and now he is working at the Tübingen in the Institute of Astronomy and Astrophysics. So he's known for his works on radiation processes in neutron stars, atmospheres with and without magnetic fields, and X-ray binaries and cataclysmic variables. And he collaborated with Nikolai Ivanovich in the works about emission from accretion disks. So Valery, welcome. Yeah.
Could I start?
Yes, yes. We see it.
Okay, great. Good afternoon, dear colleagues. I'm very proud and very glad to give this talk in this mini conference devoted to Shakura's 80th birthday. And I would like to talk about our together work with X-ray nova, and therefore with non-steady state accretion disk in these objects, and how we try to get alpha parameter in this disk using the models which was developed by Galina Lipunova and Nikolai Shakura 25 years ago. And I will present also some historical sketch how Nikolai Shakura was involved to non-steady state accretion disks for investigate this. Konstantin Postnov has given us very beautiful presentation how it working now, but my presentation was mainly historical. Sorry. Okay, it's working. I would like to start with the most famous paper, which was written by Nikolai Shakura and Rashid Suneyev published in 1993 about disk accretion on black holes. And it's famous paper and the famous photos also here. And of course, immediately after publishing of this model, many people started to investigate this model in many aspects. For example, Novikov and Thorne presented the relativistic version of this model, and many people started to investigate stability of this accretion disk. And the next year, maybe in the year of the publish, this instability of the inner parts of accretion disk where radiation pressure dominates was found by Alan Lightman and Douglas Airdley. And I'm sure that this work pushed Rashid Suneyev and Nikolai Shakura to investigate this instability of inner parts of accretion disk, of high luminosity accretion disk. And they did it very perfect. And I would like to present shortly these results. this published in this famous paper in Monthly, theory of the instability of disk accretion onto black holes. And they found that stable accretion could be only on very specific value of viscosity in accretion disk. Of course, the real viscosity in accretion disk is not this one, and therefore, in the most part of the accretion disk, in zone A, so-called zone A, are unstable. And I would like to present this famous picture for instability branches in these accretion disks. And I put here this the basic of the stability analysis, how it looks like at the present day. So it's necessary to have some steady state solution for every values in the accretion disk and perturbate that with this kind of perturbation. And then if you contribute put this perturbated values in the equations which define this steady state solution, you can obtain dispersion relation. And using the dispersion relation, it's possible to investigate in which wavelengths the system is stable or unstable. And of course, this square of frequency, if this square frequency larger than 0, and therefore you see it will be some waves in the system. And this, if this square of the frequency is less than 0, it's not real, and therefore perturbation grows exponentially. In this case, system is unstable. But it's very interesting that Nikolai Shakura and Rüdiger Staubert did not use this standard approach and invented his own method, which completely the same in the sense, but a little bit different in the realization. It's, for my opinion, it looks like the situation when Werner Heisenberg invented matrix and matrix mechanics and operation with matrix for creating of quantum mechanics. And it's, I think it's an interesting situation for that. And as a result, they found dynamically unstable branch, this low branches here. And they found additional thermal unstable branches, much more large frequency at the same wavelengths. And they found that accretion disk are unstable if this beta parameter, radiation pressure to total pressure, larger than 0.6. It's very beautiful results, but it's not the end of the story. 10 years ago, Nikolai Shakura returned to investigate unstable disk accretion together with Yuri Lubarsky. They published a very interesting paper in Astronomy Letters in 1987. They considered this diffusion-like equation for this function. It's some parabolic partial differential equation and this component and viscous stress tensor involved and specific angular momentum. And they found self-similar solution for this function y, and they considered function of f in this form, where n and m is integers, which depend on the opacity in the matter, which dominated opacity in the matter. And they considered 3 cases. They considered some ring of the matter and some radius around the accreting center, or around the black holes or a neutron star. and considered initial state how matter spread to the accretion centrum. And you see it's here, this solution. Then they considered the stage where matter reached this accretion state, and quasi-steady state situation arise, transition to steady state, and they also obtained this analytical solution for this situation. And at the end, they considered the final stage of the accretion of this ring of the matter, when the matter is exhausting and accretion fading, and also obtained these analytical solutions. So it's again not the end of the story, and the next return Nikolai Shakura to the unstable disk was connected with developing of X-ray observations. And in the in early 90s, modern for that time X-ray observatories found that there are so-called X-ray nova, and some historical nova, which was considered like classical nova. It's not classical nova, but X-ray nova as well. The most famous examples of this soft X-ray transcends is Nova Magneto-rotational 1975, and Nova Muscae was discovered by Granat Observatory in 1991. And I would like, first of all, present some results which obtained by Anna Yasinovskaya together with Ramesh Narayan and McClintock and other collaborators. They suggested the picture how accretion changes with changing mass accretion rate. If mass accretion rate is very high, therefore we see some standard alpha disk, Shakura-80 disk, and at lower mass accretion rates, some hole in the inner part of the disk appears, which filled with very hot accretion flow, very hot gas with temperature close to virial temperature, and this hole increases with mass accretion is decreasing, and they used this classification to describe classical X-ray light curves of this X-ray nova for Nova Muscae and Nova Magneto-rotational. And this nova has very fast rising and then exponential decay of the light curves. And Anna Yasinovskaya used this approach to describe visual light curves of these two nova. And they used some irradiation as a very important thing for this problem. And they found that accretion disk has to be more thick than it was suggested by standard alpha disk theory to describe this visual accretion, visual light curves. But they used some consequence of steady state accretion disks with different mass accretion rates. To overcome this simplification, Galina Lipunova and Nikolai Shakura in 2000 published a new solution for viscous evolution of accretion disks. They considered non-stationary, non-steady state accretion disk, and they found analytical solution for this accretion disk with fixed upper, with fixed outer boundary, and these properties of this non-steady state disk was used to develop simultaneously X-ray light curves and visual light curves in these two objects, two X-ray nova. And you see here that a little bit there is some difference between theory and observations due to, unfortunately, because they did not take into account irradiation of accretion disk. And at that stage, Nikolai Shakura and Galina Lipunova involved me to this work. You see here our photos together with Nikolai Shakura's family in Konstanz, nearby Tübingen and in Bodensee. And here you can see me and my wife and Galina Lipunova this year. You can see how we changed in 20 years, unfortunately. And together we considered, on the basis of the solution obtained by Galina and Nikolai, considered accretion disk around Kerr black holes and irradiation we included here, including relativistic effects. You see here how this some angular dependence of the emergent flux from inner parts of the accretion disk depends on the inclination angle, and in comparison with Newton solution. And you see here that if you observe this accretion disk face on, the flux is decreasing due to gravitational redshift. But if you observe this flux for inclined disk close to H-on situation, the relativistic Doppler boosting make flux higher than in the Newton case. And therefore, due to this relativistic effects, irradiation of the accretion disk in outer parts of the accretion disk increased in many times. You can see here the you can see here the difference. And using this approach, we computed a lot of models and tried to fit in simultaneously again X-ray light curves and visual light curves and different photometric system. And we did it using many different cases, and consider different Kerr parameters, different alpha parameters, and so on. And you see here the solutions which we obtained. The field signs show us the situation which was coincide with estimation of mass and distance to this system at that time when this paper was published. And by red strips, I show this modern values of these parameters like mass of black holes and distance to the system. And the same we made for Nova Musca, and you see that the irradiation helped, and light curves in X-ray and in optics described very well. But what's important, we obtained very large value of alpha parameter, much larger than 0.1 for the both system, and here also. And also we had to increase the thickness of the accretion disk in comparison with standard solution, in 1.5 or even in 2 times to describe this light curves. The first problem too high alpha parameter maybe was resolved in this work by Titarenko, Lasota, Henke, Deus, and Siakov in Nature 2018. They assumed that there is strong wind from accretion disk, maybe magnetic wind. And due to this wind, it's possible with the same low alpha parameter make light curve of the system more steep, and therefore to reach this high steep, we make large alpha parameter to which allow to diffuse matter very fast to the accretion, to the black holes. But if we lost some of the matter with wind, it's not necessarily so high alpha parameter, and it's possible to reach this steep light curve using low alpha parameter. In concerning the second problem with half thickness of the accretion disk, we performed work together about thickness of accretion alpha disk, and here you see half thickness, relative half thickness of the accretion disk for two cases, for very low mass accretion rays and high accretion rate, high mass accretion rays close to Eddington limit for the three B, C, and A zone. Solid lines, it's my calculations, and dashed line is a analytical solution which was obtained by Galina, and of course it's the same solution like in the Shakura-80 1973, but here using polytrope equation of state, Galina and Shakura and some student introduced some correction factor pi h, and this pi h about 2.5, and you see that from the standard theory, half thickness of accretion disk cannot be larger than 0.05 or 0.07. But from observations, we need some half thickness of the accretion disk into at least 1.5 and 2 times larger. And maybe this problem could be resolved using some matter above accretion disk due to wind and some clouds which arise due to thermal instability in the matter irradiated with hard X-rays. These models was suggested by Jimenez Gerardo in 2002 to explain some dips in X-ray binaries and narrow absorption line in X-ray spectra. And then in the next year, 2003, I am together with Fritz Meyer and Amy Meyer-Hofmeister, we used the same model for clouds above accretion disk to explain high reprocessing efficiency in super soft X-ray sources. And maybe these clouds above accretion disk can explain increased observed half thickness of the accretion disk in the investigated systems. So that's all what I would like to present here, and I would like to congratulate Nikolai Shakura once again, and to wish him good healthness and a lot of years filled with interesting scientific work together with us. Thank you for your work, Николай Иванович, and многие лета. Thank you.
Thank you, Valery. I would like now, probably we need to speed up to invite our colleagues from Kazan. These are Ilfan Bikmaev. Yes, please Yeah, and Nail Abdulovich Sakhibullin from the Kazan Federal University. They would like also to say something to Nikolai Ivanovich, as I understand. Yeah.
Good afternoon, colleagues. Good afternoon, Nikolai Ivanovich Shakura. We are colleagues of Valery Suleimanov. We continue still working in Kazan Federal University. Kazan is a city 800 kilometers east from Moscow, not so distance from Moscow. And we wish to congratulate Nikolai Ivanovich Shakura with his 80 years anniversary from all our Kazan colleagues. Kazan University has a 1.5 meter optical telescope installed in Turkey. In fact, we have only one object we investigated together with Nikolai Shakura and his collaborators is HZ Hercules, when Nikolai Ivanovich requested us to observe, to get long-term light curves near the eclipse of this object. And 5 years ago, we published it. Nikolai Ivanovich published several papers on this investigation. Most main field of our activity is more than 20 years, is optical identification of X-ray sources discovered by X-ray observatories on space. First is integral X-ray and gamma ray observatory, and now we are working together with Rashid Aliyevich Sunayev groups in Space Research Institute with the data obtained with Spectrum RG project with both telescopes, eROSITA and Arctic Sea telescope. And most majority of objects we identified from our optical observations they have a sign of Shakura and Sunayev on their astrophysical phases and manifestations, because they are or accretion disk around supermassive black holes in AGNs or around compact objects in closed binary system. But I should mention that when we worked with integral data, one of objects, for example, accreting neutron stars is demanded another theoretical approach realized in Nikolai Shakura groups. It's so-called spherical accretion to magnetized neutron stars. And it is important for us that you, Nikolai Ivanovich, and your group in Moscow University continue to develop the theory of accretion. And because we see from data from eROSITA and Arctic Sea X-ray telescopes that many other manifestations of accretion in different objects. And for example, eROSITA, its sensitivity, its higher sensitivity than previous mission allow us to detect objects with X-ray luminosities lower than earlier, 10 to 29, 10 to 30, and there are many zoe in manifestations of these objects, and we hope you will continue work in developing approach accretion process in different systems. And we need, for interpretation of our optical and X-ray data, your new developments, and we wish you good health and further successes in your work. Thank you, and we're very glad to continue collaborate with you and your group in Moscow University. Now, Professor Nail Sakhibullin wish to say some his own congratulations to you.
Yes, as I understood that we are moving to the second part of our meeting, just to congratulation part. So I'm sorry, I'll give my very short talk in Russian, and you'll understand why. Звучат сегодня громкие фанфары, но надо оценить, каков итог. пришел ли момент закончить мемуары, включив хороший эпилог. Но нет, коллеги в письмах показали, в науке пламень не совсем погас. Они во всех имейлах убеждали, что сил в Шакуре есть большой запас. Отрадно юбиляру их добрые приветы, а несколько из Казани теплых слов заложено в столь важные советы, что возраст не беда, и будь всегда здоров. Желаем из Казани вам, чтобы всегда другой, не ваш маршрут избрали беды, и будет радостна научная среда, что много дисков объяснили вы на небе. Спасибо всем друзьям, родным коллегам. Вселяем мы надежду на успех. Наш юбиляр еще возрастит научные побеги без всяких возрастных помех. And finally, I think that I wish again Николай Иванович health, especially because there are million accretion disks in the universe which are waiting, Nikolai Ivanovich, for very clever interpretation, for very overwhelming interpretation of their characteristic. Good luck you in this business.
Our congratulations.
Thank you. Thank you very much. We have also one short presentation now before we go to the second part. And as you have mentioned, Ilfan Faridovich, Kazan is 800 kilometers from Moscow. It's not the record. Today we have a guest from Japan. So this is Dr. Inoue, and he would like also to make a short contribution to our meeting. Please welcome.
Hi,
He is
thank
from
you.
University.
Can you hear me?
Yeah.
Oh, thank you.
Yes.
Hi, thank you. I'm Akihiro Inoue from the University of Tokyo. I'm an academic grad student of Professor Shinmine Shige, and unfortunately, he could not join this online meeting because of conflict with his schedule. But yes, just say congratulations here. And I would like to begin by expressing my warmest congratulations to Professor Shakura on reaching this remarkable milestone of 80 years. And our works are based on your works, so I'd like to just, yes, congratulations, yes. And okay, so I very briefly introduce our numerical simulations of supercritical accretions onto the magnetized neutron star. Okay, so accretion disk is classified into 3 types depending on the accretion rate. For example, the accretion rate is around here. The geometrically thin and optically thick is formed as proposed by Shakura and Santangelo in 1973. And our group has especially focused on the accretion regime. In this regime, in which the accretion rate is much greater than the Eddington value. And our group mainly investigated the supercritical accretion using the numerical simulations. For example, Osuga and Mineshige 2007 performed the radiation hydrodynamic simulations and showed that the supercritical accretion is possible. This numerical simulation assumed that the alpha viscosity for the angular momentum transport as proposed by Shakura and Santangelo. And this simulation also assumed that the Newtonian gravity. This radiation hydrodynamic simulation has subsequently evolved into general relativistic radiation MHD simulations like this, and they showed that powerful jets also appear around the rotation axis of the black holes. So today's talk focuses on the supercritical accretion onto a magnetized neutron star. because the periodic X-ray pulsations are detected in some ultraluminous X-ray sources. These panels show the periodic X-ray pulsations, and the pulsations indicate that at least these ULXs are powered by the magnetized neutron star. So I briefly introduce our numerical estimations of supercritical accretions. Color shows the gas density and the radiation energy density. And this is a slice of the results of the two-dimensional simulations. So we assume that the non-rotating neutron star and which has the dipole magnetic field, and we assume that its magnetic axis is aligned with the rotation axis of the disk. And the cyan lines represent the magnetic field lines. And the white vectors show the gas velocity vector for the region where the mass outflow rate is very high. And the white vector in the right panel shows the radiation energy flux vector for the region where the radiative luminosity is very high. This is the result of the numerical simulations. And after the simulation starts, gas accretes onto the neutron star due to the magneto-rotational instability. And the accretion disk forms, geometrically and optically thick disk forms around here. And the powerful radiation and outflows driven by the radiation force appear above the disk surface. And the accretion columns appears around the magnetic poles of the neutron star. And also we can see that powerful radiation energy flux from the accretion columns forms around here. Yes, before closing my talk, again, I would like to say congratulations on reaching this wonderful milestone, your 18th birthday. Thank you.
Thank you, Akihiro. Thank you for joining us today. And please, we better proceed to our next talk. And with very great pleasure, I would like to welcome Professor Jörn Wilms. Is he here?
Yes, I am.
All right. So Professor Wilms is a professor of astronomy and astrophysics at the University of Erlangen-Nuremberg, where he leads the group at the remote observatory of Erlangen Center for Astroparticle Physics. And he and his group collaborated extensively with Nikolai Shakura, co-authoring about 30 papers together for many years. Please begin.
Okay. So you should be hearing me.
Yes, we see and we hear.
Okay, perfect. Yeah, so I hope you can hear me well. I can't speak too loud. I'm right now in St. Louis in the United States. And there are the people here in the building who are still sleeping because it's a bit early. So thank you very much for the possibility to present a recent result that was done by students in my research group mainly, on a topic that is related a lot to work that Nikolai has also done. And I hope to perhaps interest you a bit into looking into this a bit more. So this is a talk that is mainly observational, so it will not have equations, even though we all know that Nikolai usually likes to look at equations. And this is a beautiful example here from one of the visits that Rüdiger and I had to Moscow, and this is another one. And you also see that it's very difficult to have photos where Nikolai is not looking at either equations or data, which is, I think, also very characteristic and also a very good overall characteristic of researchers in general. So it shows the overall enthusiasm here. And some of the enthusiasm was also that I always felt very welcome in Moscow, even when I was still a grad student, and also felt very supported by all of our collaboration. And so when thinking about what should I be talking about here, there were various options available, and I decided to use a topic that has to do with eROSITA, because that really was for a very long time a beautiful joint collaboration between Russia and Germany before politics unfortunately made us to stop all of this. And eROSITA has resulted in a huge amount of very interesting data that are related to accretion flows and accretion physics in general. And I believe that this is a very nice result here that I'm going to present about the survey of ultraluminous sources in the eROSITA survey, or rather on the German part of the eROSITA survey. This is a work that includes a lot of people which are listed here. The primary driver behind all of this is Philipp Weber, a student of mine. The underlying papers here will be submitted in the next couple of weeks or so. So this work has not yet been published. So why are we interested in ultraluminous X-ray sources? And why is eROSITA such a very good instrument to do this? Ultraluminous sources are formally defined as point sources in X-ray images of other galaxies. They are somewhere, but not here in the center. We know that there are ULXs in the centers of galaxies, but since active galactic nuclei are also in the centers of galaxies, if you look for ULXs, you better don't look there. And there are sources who have extremely high luminosities in the super-adding luminosity regime of 10 to the 39 ergs per second or more. Many of the ULXs are transient, many of the ULXs are variable. You do not see the ULX here in this optical image. This is the same image now of this galaxy in the X-rays done with Chandra in this case. And you see that suddenly here at this location, there are two beautiful bright sources. And this is exactly how you find ULXs. You try to search for them in the X-rays, and you try to look for very bright sources that you can that you see in these galaxies. So what are ULXs? There are really two possible scenarios. One of them has been very surprising a few years ago when people started to look at them and detected pulsations in them. And these are very indicative of these objects to be neutron stars, but not neutron stars like Hercules X1 that Rüdiger presented, but neutron stars that have super Eddington accretion, because they're far too bright really for any standard Shakura-80 disk. You really need to go at the very, very high luminosity regime and understand their phenomenology there. And that's why we also have to observe them. However, the alternative, some subgroup of the ULXs are also much brighter than stellar mass black holes, but they're fainter than AGN. And an intriguing alternative for one of these subclasses is that they could also be intermediate mass black holes, which are somewhere between stellar type black holes and active galactic nuclei. So this is why these sources are so interesting. It is a mode of accretion that we can't access otherwise, and we also, to be honest, don't understand how they work. So the best way of going to understand these about 2,000 ULXs that we have, that we know right now in about 1,000 galaxies surrounding us, is to do some inventory of these sources. And this brings us to eROSITA. The reason for this, and why eROSITA is such a good instrument for us to look for ULXs, is that eROSITA performed an unbiased all-sky survey. You all know eROSITA was launched a few years ago now, and then performed about 4 surveys of the overall X-ray sky. So contrary to all missions since ROSAT, eROSITA has really been looking at all of the sky and not only at selected sources. And that means that we can perform an unbiased search for Yule X's rather than having to rely on people to look at the galaxy and then detect a point source there, right? And this observation, which are underlying most discoveries of Yule X's, have the big problem. Typically, you select galaxies not because you want to search for Yule X, but you select them because they're interesting for some other reason. And that is exactly where this bias comes in. So how do we do this for eROSITA? We know, well, Yule X's are located in galaxies, so we need a galaxy catalog. And thankfully, since a few years, there's a very beautiful catalog called Hecate, the Heraklion Extragalactic Catalog, available to us, which essentially lists all of the 200,000 galaxies that are within 200 megaparsecs of us. The catalog is very useful for the work that I'm going to present because it also includes a lot of additional information about galaxies, from the optical luminosities, the mass of the galaxy, their star formation rates, and also things like the sizes, the so-called D25 region, so the border of the galaxy. And here's a nice example of what a galaxy does look like in Hecate. Well, this is an underlying image. For us, a galaxy just is this ellipse. So these are the 100,000 Hecate galaxies, which are located on the Western Galactic Hemisphere. So the part that we on in the German team of eROSITA have access to. Now, what you can see there is a combination of the in the distribution of the galaxies is a combination of large-scale structure. So you see these strands here where you have galaxies that are located really physically along a region in the universe. You see an exclusion zone here behind the Milky Way, where we know fewer galaxies because most of the light is absorbed. But you also see, for example, a change in the density of the galaxies here, and that is not real. Also, you see in the south, there are fewer galaxies in Hecate. And that just has to do with the fact that you have deeper surveys, optical surveys in this region and not down here. So we know that there are more galaxies down here, but we don't know where they are. So out of these about 100,000 galaxies, if you now look at all of the X-ray observations that we've done with pointed observatories, you find that about 30,000 galaxies have already been looked at. This might appear like a very large number, but this has to do with the fact that many galaxies are serendipitously in the field of view of observations or another object. And so the overall number of galaxies that we've looked at in the X-rays is formally very high, but most of these have never really been understood. Have never really been analyzed. Now, how do we go about to search for ultraluminous X-ray sources with eROSITA? Well, we take these 100,000 galaxies here, and then we look at the eROSITA data from all of these objects. And we then look for eROSITA detected point sources, which are located within the galaxy, meaning within this ellipse here. We decide that there are point sources which we can really detect with eROSITA, which means that their detection likelihood is high enough, so we have enough photons that we can really see the point source. They must obviously be located in the image of the galaxy, so within the D25. They must be away from the center of the galaxy, and we define here as an exclusion zone 12 arc seconds. And they must have a luminosity of larger than 10 to the 39 ergs per second, assuming that the point source is at the distance of the galaxy. And if we have enough counts, we then also characterize the spectrum of that point source. Now, these criteria are first criteria to find the sources, but the problem is there are other sources also which could look like ULXs, so-called contaminants, right? So, for example, you have supernova remnants in these galaxies, which could have a similar luminosity, but you could also have active galactic nuclei, which are farther away, but far more luminous, and might appear like a source that is in the ULX range if that point source was at the D25 region, right? So we have contamination, and we have to deal with that contamination. So, but before we do that, let's first take a quick look at one of these galaxies that illustrates some of the challenges if you want to do that really observationally. This is NGC 1824, 12 megaparsecs away. This is a very clear point source in this source, and this is a new ULX candidate that we detected there. And I guess everybody can notice this is a very bright source. Now, if you look on the optical image here, you see the location, right? It's far away here from the galaxy. It looks smack on the galaxy, and we're very sure that this is a proper object. What you also see is that galaxies are not always ellipses, and that the D25 region for this galaxy really does not characterize the shape of the galaxy. But unfortunately, there's not much we can do about that. So for us, all galaxies look like ellipses, even though most galaxies do not. But most sources are not as clear. And this, for example, here, you see this bright pixel here behind the red circle. That is more a typical type of an eROSITA ULX detection here, which has a fairly low detection likelihood. It still is in the galaxy here. It is in the outskirts. But with just the eROSITA data, we can't say much more than estimate its potential luminosity. But this is still very valuable because this gives us sources which we can then follow up in other observations. The problem now is that we have many of these faint sources, and statistics really doesn't work that well on deciding whether a source is a ULX or not. So we did some kind of a sociological experiment, and that sociological experiment was more or less that we gave images like the ones that I showed you before to a number of astronomers, really literally just forcing people at the observatory and elsewhere to look at these images and make a decision of whether what they see is a galaxy or not. And then to classify these sources, and each of our candidates, and there were hundreds of them, was looked at by at least 2 people. And what you see here now is the statistics on the detection likelihood. Is this a real source versus the probability that somebody of the people said, yes, this is a proper source or not. And what you're seeing is that this red structure here goes down. This is the number of sources where both people said, no, it's not a galaxy. And this is where at least a ULX, this is where at least one person said this. And so in the end, based on this visual inspection, we decided on a threshold above which we believe or do not believe a ULX. So this was quite interesting, right? This was a very good use of massively parallel computing with the brain rather than using a computer, and it was very useful. So we have 2 samples of ULX candidates, one that is in this regime and detection likelihoods between 10 and 20, where the sources can be kind of something else also, and a sample where we are very sure that these are ULXs. And to give an overview over the sample of sources, what we show here is the distance to the source and the luminosity. These 2 lines are the sensitivity, so sources which are fainter than this line here in a typical eROSITA survey, or so in a typical eROSITA survey would be difficult to find sources which are fainter at a given then this line here can only be found at the survey poles where we have a larger exposure. You see there are some sources that fall below these lines. This just has to do with regions in the sky where we have better observations. So what you see here is clearly we detect faint sources only nearby and more luminous sources only farther away. There are few very luminous sources nearby just because the volume that's covered is small and they are fairly rare. And you see blue and red colors here. The red colors here are new eROSITA candidates. So these are ULXs which have never been published in the literature. The blue ones are sources there are sources that are somewhere where we've never looked at before, so they're really completely new. We have 260 of these candidates, 245 are completely new. If you now look at the better sources, the ones with higher detection likelihood, you obviously have fewer sources, and we have 85 of these candidates, and 53 of them are new. So some have exposure with other instruments. So some are in galaxies that have been seen before, but we have not, but weren't published. And this typically has to do with the fact that we know that ULXs are luminous, are variable. So so the fact that a source has not been detected before also tells you something, namely that these very luminous accretion flows are extremely variable and not just static. You may ask, okay, do we also detect ULXs that have previously been known? And the answer for this you find in this diagram down here. This is a distribution of the cataloged luminosities of ULXs of the 2000 ULXs. You see many of them are so faint that we would have not detected them with eROSITA, but there are enough there that we could detect them, and we detect a certain fraction of them. The ones that we don't detect, again, are ones that are variable. So this all works well together. And you might ask yourself, why do we care about finding 85 or so new ones, given that we know a few thousand of them? And the reason for this is the beauty of the eROSITA survey, and that is we really look at the whole sky and we can understand very well the survey sensitivity. So we can tell you for each source with very high statistical precision of whether we would or would not have found it. And this is illustrated here based on simulations that we did. So as a function of this short exposure time, this is the limiting flux above which, as a function of this detection likelihood, we would have seen a source or not. And that is really nice because this means we can compute for each galaxy in Hecate, for each of these 100,000 ones, what the limiting luminosity is for this source, for this galaxy, and that means we can correct for all of the observational biases, and that is far more difficult in other searches for ULXs. So this is shown here on the left-hand side. This is an exposure map that tells you the sensitivity and the detection likelihood, and this is the distance up to which we would have detected ULXs. And so you see in the whole survey, there are 519 galaxies only where we would detect ULXs at a luminosity of 10 to the 39, but there are 100,000 where we would have detected the very, very luminous one. This just has to do with the fact that you can see brighter sources over larger distances, right? Now, this is one thing we can do, and I always spoke now about ULX candidates, and the reason for this is that we have contamination, so we have AGN and the supernova remnants and so on that I spoke about, but the really biggest contaminant is active galactic nuclei, and so we need to understand how many active galactic nuclei could appear like ULXs in our galaxies. And because we know the sensitivity for our detection in each given galaxy, we can now take the statistical distribution of AGN, the log n log s, and compute the probability that we would detect an AGN with a proper in the proper count rate range in the area of a given galaxy, and we can sum this up in a statistical sense, to estimate how many active galaxies we have as contaminants. And what we find is that we have a strong contamination. This is well known. This is also the case for other AGN, right? Of 30 to 50%. This sounds large, but the beauty is because we know the sensitivity so precisely, we can correct for that when doing statistical analyses on the behavior of ULXs. And for example, we can compute the luminosity function. So what is the number of sources brighter than a given luminosity in per galaxy? This is the first time that somebody has tried to do something like that with this precision. Typically, you find luminosity functions with some corrections, but doing this on a per galaxy basis with a large number of galaxies we probed is really something very amazing. So you find about 0.049 ULXs per galaxy. The distribution here is proportional to the luminosity to the minus 1.22. You see it's not turning over at the lower luminosities, indicating that we are complete. And you see that there is an indication that there might be a turnover in here. And that is something now that is a challenge for people who do accretion flows. And many of them are listening to this to really think about where this type of the luminosity function really comes from. So this is a beautiful example. Others have tried this before. Even cooler, in my opinion, is that since we know for each Hecate galaxy the type of the galaxy, and since we can correct for the AGN background, we can compute the fraction of the number of ULXs as a function of the host type of the galaxy. And what you see here, for example, is that we do detect in a statistically significant way also ULXs in early type galaxies, so type E and S naught. And these are galaxies where there is no recent star formation. So these are ULXs that are that cannot be in high mass X-ray binary systems because all high mass stars in these galaxies have already exploded. So these are ULXs which must be in low mass X-ray binaries. This is something that where there were indications already in previous work, for example, by Hugo Tranin, but we now have a much better statistics down here. And we also see a distribution here among the spiral galaxies, and you see this trend that towards later types, we have more of them. This has to do just with the structure of stars in there. But I would like to challenge people who like theory to think a bit more on how you can make ULXs in a low mass X-ray binary system and how you can power them for such a long time that this type of a statistic that we now find with eROSITA is can be reproduced in data. We have far more than that, but my time is over. So just to summarize, we find 245 weak ULXs, 53 very strong cases, which nobody has ever looked at before. There's a lot of evidence for variability there. If the slope in the XLF is real, we have evidence for two classes, high mass and low mass X-ray binaries. We find in late type galaxies that are more low luminosity ULXs, early ones in high luminosity ones. I did not show radial profiles, but the distribution of the galaxies over of ULXs over the galaxy is what you expected. And the next steps for work, and hopefully we can also start working with people in theory again is on the observational side to do the follow-up, but then also to understand far more the accretion physics at these highest mass accretion rates than what we do so far. And with this, I would like to conclude, and I would also wish you very much a happy birthday again, Nikolai, and may you always continue looking up to the stars and enjoy the stars and the beauty of the universe. Thank you.
Thank you. Thank you very much, Jörn. That was beautiful. Yeah, a lot of to think about, to model. Let us go to the next talk then. So we should move. So I would like to introduce Professor Andrea Santangelo. He's a professor of high energy astrophysics at the University of Tübingen and the director of the high energy section at the Institute of Astronomy and Astrophysics. And I should say that also the group of Professor Santangelo has long relations with Russian scientists, and this was ever the fruitful collaboration. So welcome.
Thank you very much. Can you hear me?
Yes.
Now I share the screen. Can you see my screen?
Yes, it's in the presentation mode. Thank you. Yes.
Yeah, it is in the presentation mode.
Yes.
Galina, thank you very much. And Nikolai, I was very happy to make it because this was the first days after my long sabbatical of 8 months. It's the first week of the semester. So, everything has to be done in this first week, but I moved around things in order to be here and to celebrate you. And it's true that there is a long history of collaboration. Now, from Nikolai Shakura to eXTP, from a man to a mission. But the truth is that the work of Nikolai Shakura and Nikolai have been a guiding spirit for the people that today are involved in eXTP, and also for the physics and astrophysics that we want to do with this mission, the enhanced X-ray timing and polarimetry. When I was back from Columbia University working with Bob Novick there on polarimetry, and I was back in Italy, and Livio Scarsi with Beppo Sachs told me, now you have to work on galactic sources. I said, but I know not too much, no, but you have to work on cyclotron lines, accretion paths. And I said, okay, but this is accretion. So I read this, which I consider a masterpiece of high energy astrophysics. So at that point, Nikolai and Shakura and Tsunaida became like two big names in my personal pantheon. And then when I moved to Tübingen, I had the opportunity, since I'm the successor of Rüdiger Staubert, I apologize, Rüdiger, that I could not attend your lecture, but, I saw that there was this collaboration between the Sternberg Observatory and Tübingen. I was not really part of that work, but this was the chance to know Konstantin, of course, and Nikolai Shakura. And this is Nikolai, which is presenting work at the meeting in honor of Rüdiger Staubert's 8th birthday, which was in Tübingen. And of course, he was working optical data, but on Hercules X1, which should not be surprising in the end. So, however, this has not just been, science and talk. We had a nice dinner here, Nikolai with Natalia, with Ushi Staubert, with my wife, and I think we are at Staubert's place for a nice dinner together. So it was kind of a friendship, like I developed then with Konstantin. Accretion is still to be fully understood in strong magnetic field. Super-Eddington accretion is now, I believe, a real new frontier. We have to understand what's going on. And this is a long story which continues through many generations. eXTP, which I want to present, fundamentally is related to accretion. This is the enhanced timing and polarimetry mission. The mission is passing the PDR now, which means is entering the construction phase. And it's not like your observation, it's not the equation, but it's instrumentation that, as you know, was a strong part of Staubert's group and is a strong part also of my group. And this new set of white papers has been published on Science China. And of course, it's on the fact that eXTP is planned to be a machine for extreme physics. Dense matter, which is the state of matter at supernuclear density. Again, we detect quark stars or other exotic stuff. Strong gravity, what are the properties of space-time under extreme gravity? Can we detect the deviation from Einstein general relativity? Strong magnetism, behavior of the light in the presence of the ultra-strong magnetic fields. Can we see the effect of QED and show them in the stars? So it's physics and astrophysics of the bright sources. But not only that, there will be a lot of observatory science and, of course, multi-messenger and time domain astronomy, like synergies with gravitational wave. Now, eXTP is not the old eXTP because the European, due to geopolitical circumstances, were not allowed to participate. This is the true story. Even if the funds were allocated, it was prohibited. I mean, the country said we don't deliver hardware to China, but still the scientists are participating. And it's now, there are the spectroscopy focusing array, the polarimetry focusing array, and the wide field, the wideband camera. I mean, these are the optics of the SFA, but also of the PFA, and they are based on nickel electroforming, but that's not relevant. What is relevant, you can see in this slide, is that there are actually two types of instruments, the SFSI timing and the SFA imaging. And then there is the polarimetry focusing array. As you see, they have different field of view. The difference between SFA timing and SFI imaging is in the detector. This is the traditional detector, the STD, used for the timing. And now we have a unit which uses the eROSITA PN CCD. So it's capable of doing imaging. It's a new addition recently. Okay, but this perhaps is too technical. I don't want to bore too much Nikolai. So I move on the next slides, which says, okay, this is the comparison of the effective area, Athena, and eXTP SFA. But we have to be careful. This is post-2037. I say hopefully, but I'm very confident that Athena will be adopted. But this is post-2037. And therefore, the reality in next decade, for the larger part of next decade, is that we will have such a machine which is going to produce a lot of photons. It is not only spectroscopy, it is polarimetry. This is the PFA. You know, polarimetry has been opened by eXTP now, and this is a great success. It's posing us theoretical problems, which still we have to solve it. Now, the PFA on eXTP will bring polarimetry to a post-eXTP mature stage. You can compare the area, and you see the difference in effective area between the eXTP PFA and eXTP, which is significant, which means that polarimetry in the next decade will be, most X-ray polarimetry, of course, will be eXTP. It's a unique opportunity for a golden age of X-ray polarimetry. Now, science. You can look at the white papers, but you know, the first core science is the interior of the neutron stars. What is the equation of state? And in the equation of state, to solve this problem, you can look at the white paper. Actually, the difference between the NICER and the eXTP is not only in the sensitivity, but also because we will apply a symphony of techniques on different sources, on the same source, in order to try to constrain the equation of states from different point of attacks. And observation will probe a diverse range of X-ray sources pulsating. This is just to give you an example. It's the difference between NICER observation and eXTP SFA observation of the pulse profile. I'm referring to the pulse profile modeling technique, and also the difference in the background, with respect to the signal in the background. We know that the controlling of the systematic of the background is enormously important. And so just on this source, comparison with NICER, this will be the increasing in the constraints that we will get. But there is much more, because we don't have to forget that there is a polarimeter on board. And therefore, we might reach a constraint on the geometrical parameters of the neutron stars, which are much better than those of XP. And in the end, if you look to the constraint on mass and radius that we can provide, they are quite robust, 1.3 plus 0.06. So truly, we will have a new era. Of course, when we talk about accretion, remember the first paper that I showed, we have to talk about black hole. And it's complicated. There is always accretion, but there are hypotheses, the corona, the spherical corona, the sandwich corona, the reflection of the photon, maybe second reflection, and so forth, so on. So it's a complicated astrophysics in physics. This is just an example. On the left, with respect to XM and Newton, on the right, you see the capability of the SFA to constrain using X-ray reverberation mapping the mass and the so-called altitude, let's say, of the corona. And there will be the capability also to measure, to constrain the spin using X-ray polarimetry. And you see, significant is the difference in the values of the polarization degree and in the values of the polarization angle, depending on the angular momentum of the black hole. We can also try to measure the spin through thermal continuum fitting. And if you look what eXTP can reach, which is that blob, red blob in the center of these contours, this will certainly imply a jump in our understanding of the spin of the black holes, which is an open issue because there are differences with those we measure from gravitational waves. I mean, there is work to be done. But we look also for exotic physics, that should be our horizon, something totally new. And this is just a simulation of the constraint that you could impose on the Johannesson deformation parameters with respect to the spin in case of beyond gravity theories. I know Rüdiger has presented pulsars, and here we want to test the correctness and the geometry of the rotating vector model and push the theory behind the polarization emission from pulsars. But also there will be way to test the neutron star precession, like the origin of superorbital variability might be related to the precession of the neutron star. And eventually also using accreting neutron stars to test the vacuum resonance. I'm not talking here about magnetars because I wish to focus on these accreting pulses. Now, accretion, for which Nikolai Shakura has provided the fundaments, is still a key physical effect. And it's the effect which provides the playground through the observation for fundamental physics studies. eXTP will produce groundbreaking results on the physics and astrophysics in the extreme playground of compact objects. But I want to say something else, other conclusions. and it's more from the collaboration and human point of view. Thanks to Rüdiger Staubert and Nikolai Shakura, the collaboration with the Russian scientists, of course, especially with people in Moscow and with the Sternberg Observatory people, has been an incredible adventure for Tübingen. And my assistants like Dmitry Klochkov, Viktor Doroshenko, but other students like now his postdoc, Artur Avakian, Andrei Tavlev, and Rosalia Doroshenko, and Valery is with us, is the result of this strict collaboration. The contribution to science of this Russian Moscow school has been enormous for Tübingen. And I always look to attract the best students from there. And this is not ultimate. The collaboration with Yuri Putanen, Valedina, Sasha Valedina, and Sergei Zigangov. They got a Bessel Prize from the Humboldt and stayed in Tübingen. Is now very strong and producing results. And we are going to organize, will be announced in the next days, the first week of September 26, the first eXTP conference after construction, I mean in the construction phase in Turku and in Finland. And Sergei is doing an incredible work of that. I was able to connect strongly the Turku group with the Chinese group, and this will be extremely fruitful. As I said, this is the result of two people, Rüdiger Staubert, you see from the back, and especially Nikolai Shakura. And then I want to say thank you, Nikolai, and happy birthday, Nikolai. Thank you very much.
Thank you, Andrea. Thank you very much. Thank you for the great talk. I'm so happy we've heard today so many talks which showed us the lifelong evolution of models and the relation to observations and numerical simulations and the big future that these models will have and new models should have, and a lot of to model for Nikolai. So more to come. That's not all. I have also not shown yet a short presentation from one of the students of Nikolai Shakura. She is in US now in the Colorado Boulder University, and she wrote her video. Let me show you. I'll try to I hope you see the picture.
Yes, we do.
Yes, and now I'll try to play, and I hope you'll hear her voice.
Dear Nikolai Ivanovich, happy birthday. I'm so glad to be part of this celebration today, even virtually. You remember when I was just a student, I graduated from university, you invited me to join your group in Gaish, and I will always be very grateful that you saw me and believed in me and gave me that first opportunity. Without that start, my life might have taken a completely different direction. Because of you, I stayed in science, and I still feel the influence of those early years of everything, in everything I do. Working with you and seeing how you work with other people taught me not only how to do research, but how to think about it with curiosity, precision, and respect for the facts. I always remember your calm, thoughtful approach and the way you encouraged young scientists to find their own path. Sometimes I even dream that I come back to Gaish, meet you there, and tell you about my current projects. It's a warm and inspiring dream for me, and I really hope that one day it will come true, and we will see each other, not only on Zoom screen. Thank you for everything you have given to me, to your students, to your colleagues, and to science itself.
Okay, thank you. That was Anya Chashkina. Also, there were many people who sent their greetings. They couldn't come today to this meeting. This is Andrea Merloni. This is Andrzej Zjarski. This is Agnieszka Januik. This is Alexander Petrov. Of course, Rashid Sunyaev. So let me just pass these greetings to you, Nikolai Ivanovich. And these people wish you good health and new ideas and many works. So on behalf of everyone, I'm just happy that we met today, and like to congratulate once more Nikolai Ivanovich with this tea. And drink to your health. Yeah. Also, if Sergei Borisovich, on a final note, have a little extra presentation for a minute. Sergei?
Yes. Hello, everybody. Can you hear me?
Yes.
Yes,
Perfect.
we do.
As Anna said, it would be nice to see each other in person, but still we are astronomers, and there is a very interesting possibility to look at Shakura. You can do it nearly every night. So there is an asteroid called Shakura, and now it's perfectly visible, at least from Europe. So if you have a telescope and you're sleepless, so you can go and have a look at the Gemini constellation. So you see coordinates here. Some more details. The object now is not very bright. It's nearly 19th magnitude. So it's slightly less than 2 astronomical units from the sun, actually. And so that's the visibility from Central Western Europe. So you see that around 2-3 o'clock in the morning or later, you can perfectly observe it. So that's the map for Moscow. So you see Sirius on the south, Orion, nice moon would be visible, Jupiter, and slightly above the Jupiter, you can find the asteroid 14322, called after Shakura. So also congratulate Nikolai Ivanovich with his birthday and bring my best wishes. And thank you, everybody who listened for the seminar. Thanks to Galina, who organized all this event and was our chairperson today. Thank you.
Thank you, everybody. There were 4 organizers of this event. So Sergei Popov and Konstantin Malanchev and Valery Suleimanov took part in it, very big part. Thank you, everybody. So goodbye. See you again.
And see you in Moscow next time, I hope. Okay.
Okay.
See you.
See you.
Okay, yeah.
Bye.
Happy birthday,
Goodbye,
Nikolai.
everybody.
Bye.
Thank you very much.
Bye.
Thank you.
Bye.